Okay, this is going to be a little experimental. I apologize if this doesn't work out beautifully, but I did this before and the audio got lost, so what I'm going to do is just use the same sheets that I had before. First thing I want to talk about, we're going to really introduce right now electric potential, and this is sometimes called potential difference and sometimes called voltage. And the symbol is V, and the unit is volts, which also has a symbol V. So when we're talking about electric potential, it's useful to think of potential energy, U. Okay, and when we talk about the potential energy for a conservative force, that means a force where if I have an object here, if I move it around, bring it back here, only against that force, then I'm going to have the same potential energy that I started with. So in other words, it only depends on the position relative to the conservative force. And electrostatic force is one of those. And so if we simply talk about having a, let's say, a positive charge here, and that's fixed in space, that's riveted to this table. Okay, if I take a positive test charge, let's say it's the head of this pencil, the eraser of this pencil, and I bring this test charge close, I have to do work. Okay, so if work by me is positive, then the change in potential energy due to the electrostatic force is also positive. And the work done by the electrostatic force is negative. And we know this because of this. The force of the electrostatic force, the direction of the electrostatic force is outward. We're moving it inward. And so the dot product ends up being negative. And that's the way I always think about these. I always think about what work would I have to do? What would that do to the potential energy? The electrostatic force would give work in the other direction. In other words, it would be a negative work. I shouldn't use direction because these are scalars. Well, that's potential energy. So the closer you get with a positive test charge to a positive charge, the more potential energy there is. So similarly, if we have a negative charge and bring it in, there's less potential energy. It wants to be there, if you will. Okay, it wants to be close. Now, electric potential, V, is just, let me say this, the change in electric potential is simply the change in potential energy divided by what charge you are moving. So obviously, if the tip of this head is a nanocoulomb, bring it close, I have to do a certain amount of work. If it's a coulomb, I have to do a whole lot more work. Okay? So this voltage or potential difference or electric potential, or just potential, the change in potential there, is related to how much potential energy is required and what the charge is on there. You can think of this somewhat like the change in potential energy for an object up on a hill. Okay, we can say if we call the ground zero, which we don't when we talk about gravitation usually, but just bear with me. The higher it is, the more potential energy it has. We can't say, based on the height, we can't say how much potential energy this thing has unless we know its mass or its weight, mg. And if we had the mg, we could think of just plugging in the m, and we could figure out how much potential energy it is just by knowing its weight. If we think of that with charges, it's the same sort of concept with voltage. Okay. You could think of it as the higher you are, the more potential energy you have. The higher you are, the more, if it was a charge type thing, voltage that you have. And I realize it's a flawed analogy, but it's just a way of thinking about it. And very frequently when we're thinking of circuits, it's helpful to think of these as being higher, and so having more potential energy per unit charge. Okay, now let's move on. I like this map here. This is something that helps me keep all this stuff straight, and I'm going to walk you through it. Okay, this is the electrostatic force, and we know how to get that. That's K times Q divided by the distance between them squared for point charges. Okay, if we find the work, that's the integral of F dot dr. the work done by the electrostatic force, multiply it by -1, and we get the change in potential energy. Well, what we could do is simply plug this in as negative integral of F dot dr, and you get delta U. Okay, if we divide that by Q, we get delta V. Well, that's kind of similar to what we used to do over here, right? If we take the force and divide it by the test charge, then we get the electric field. So there's a certain symmetry here. Okay, force divided by a charge equals electric field. Delta U, in other words, change in potential energy, divided by Q gives you the change in electric potential, or the potential difference. Similarly, we can integrate this force and have negative F dot dr equal the change in U. But think of this, force divided by Q is E. So we could actually integrate negative E dot dr and get delta V. And so what happens on this whole thing is it gives you a structure for remembering how these guys are laid out, how these work. Now, if we look at voltage from a point charge, we want to figure out the voltage at any given point relative to infinity. As if we bring it in to infinity, how much work from infinity, how much work it takes to get there, right? And then the voltage, that would be also the negative of the change in potential energy. But the voltage, we can just do that more easily by integrating the E field. So let's bring this thing in. We have to do, there's a certain amount of voltage, a certain amount of potential energy change per unit charge to bring it in from outside. So what we're going to do is we're going to integrate from infinity to this distance r of E dot dr. And if we do that, infinity to r of kq over r squared dr, and that's negative. And that's negative integral there. I've just rewritten it for some unknown reason, but it's kq over r squared. That's the exact same thing. I apologize. When we integrate this, we get kq over r, but it's negative. The negatives cancel. And ultimately what you have when we evaluate that from infinity up to r, we have kq over r minus kq over infinity. Infinity is a very large number, so this ends up going to 0. So we end up with a voltage of kq over r for a point charge. And I should have made this as a delta V. But again, if we call infinity 0, then the absolute voltage would be K times Q divided by R. I apologize, I'm going between capital Q and little q. I really meant the capital Q all the way through. And that's a very, very useful thing for a point charge. If all we have is a point charge, this gives us the voltage at any point outside that. It ends up being useful because we can use superposition to add the effects of multiple different voltages. So let's look at this problem right here. We have capital Q and little q, and their distance r1 and r2 away from point P. And we want to find the voltage at point P. Find voltage here. Well, all we have to do is say the voltage here relative to this, if we ignore the little q, is just going to be kq over r1. K capital Q over R1. Now let's ignore that one and use this one. The voltage here is going to, the voltage here relative to Q is going to be KQ little q over R2. We add them together and we get the total voltage. That's the concept of superposition, and that can work well for you in slightly more complicated problems if you keep your wits about you. And in the next video, I'm going to talk about electric potential with spheres and shells, conductive spheres and shells.